Okay, so up to this point, we discussed about the use of survival function, and now we can integrate those things that we have discussed into a proper notation, which is frequently used in actuarial calculations, because as we have seen, these are probabilities, but it's like it's very convenient to work with a proper unique set of notation. Then you can apply it in worldwide without any um, further like misunderstanding. Because even for some probability books, you will have uh, few different notations in depending on the time of that book or the publication of that time. And but the actuarial notation, so it's kind of a unified framework. So anyone in any part of the world can understand it properly without even though you don't know like much about the distribution theory. So you can work with the actual, which means the notation, to calculate some probabilities. But if you are going beyond and do some calculations and simulations as an actuary, so you should have sound knowledge about the probability and distribution theory, the financial mathematics, and also uh, some parts of economics to understand about these investment tools and how uh, these interest rate calculation works in different kind of economic scenarios. But the notation is simple. So in this course, we are like discussing about the notation and the probability calculations and do some um, bit advanced calculations later on. But we are not going beyond that. So in some of these examples, it might introduce some concepts, but it's only for your like clarifications and knowledge. We don't test those things uh, in the pyramid of the uh, course, but we will discuss some points which are additional. So if you are interested in pursuing like actuarial exams and pursuing the pathway, so it might be useful for future exams. Uh, that's why I have included some parts. But in this section, so it's the most basic and most important thing. So we will discuss it in here. So as I mentioned, so we need these probabilities to calculation the expected values or the occurrences of events. Um, in the previous section, we discussed about the cumulative probability and the survival probability. That means we can have a proper notation for that one. Um, the first one is comes to mind is the probability of surviving, because that's the event, the main event that we are interested in, not the death. So we use P, and whenever you see a P with two subscripts like the Px to T, that means we can define it like this: the probability of a person who is at age X and then surviving for T years. So that's how we interpret it. So there's an order. So we first interpret this and then goes to this. So that's how the order goes. And it says probability of a person who is at age X surviving for T more years denotes the probability that the life age X now survives for T years from now. It is same as the probability that the Tx, because the age is X, so the future lifetime variable denotes Tx, and Tx is greater than T, and it is Sxt. So we know the probabilities of Xxt, and we know how to calculate the probability of Tx is greater than T if we know if we have the density function with us. We can calculate this directly with the integration. If we know the survival function, we can use that as well. And when t is equal 1, we are not going to write it specifically. So whenever you get px1, so you can write it just Px. So it says the probability of a life at age X survive for the next year. So that is the first notation we use for the survival probability indication. And then the other one is, if you know the survival probability, the other quantity is death probability. And we denote it using simple Q. Q is the probability of death of a person who is at age X, and the death occurs within the next T years. So starting from X, we count T more years. So you can see we did some illustrations using the lifetime, using a number line representing the life as the numbers. So we illustrated in here. So Q is for the death probability, and by its definition, it says if the person is at age X, so the time to death or the future lifetime random variable is Tx, and since the death occurs within the next 3 years, so the future lifetime, the maximum of the future lifetime goes to T. So then the probability is the probability that Tx is less than or equal to T. So that is the cumulative distribution function, and we write it like this: the age is X and surviving for T more years. In here also, if the person is at age X and surviving, or the death occurs within the next year, we write it like just Qx. So these are the two things that we need to in mind, and we know that by definition, uh, 1 minus fxt equal sxt. That means you can have pxt plus qxt equal to 1. So that is one more useful uh, expression we can think of building the axioms of probability and the actuarial notation. So we will discuss those kind of equations in the next few parts. So that is just kind of an example that we can write of the axioms of probability using the actuarial notation. So, and the other one is the deferred probability. As I mentioned in some examples at the beginning of today's lectures. Um, so we had that example, deferring the payments for 5 years and then for 1 year and continuing for 4 years, and the benefit payments is deferred for 5 years and starting from the 5 years and continues up to 10 years. So likewise, then if we are interested in the death occurs in between particular interval, so we call it a person who is at age X. So this is the probability of death for a person who is at age X and dies between the age of X plus T and X plus T plus U. That means this person is at age X and surviving for T years, and the death occurs within the next U years. So if I illustrate this one, the illustration shows the person's age is X and survives up to this point where T, so this is Tx, this is age. So above the line, it's Tx. Below the line, it's age. So age is X. So X plus T is the age. And at age X, the Tx is 0. At age X plus T, then it has to be T. Then after U more years, this is T plus U. So this gap is T and this gap is U. So Tx is T plus U. Age is X plus T plus U. So the death occurs in this interval. So that is the so we are calculating the probability of that event, and it is denoted by Qx and surviving for T years, and death occurs within the next U years. So those are the three useful notations we can use in these probability calculations. So P is for survival probability and Q is for death probability. And now let's quickly go through an example given in here. Um, we are asked to express the probabilities associated with the following events uh, in the notation. A newborn infant dies no later than age 45. Let's draw a line for this one. Since the infant is newborn, age is 0, so that Tx, and infant dies no later than age 45. So age is 45, and Tx goes to 45 as well because it's starting from 0. So Tx also equal to 45, and that is the region where our interest event, or the margin of the age or the future lifetime, where the interested event begins, or the event timeline for the interest event is uh, set to begin at this point. So since it is dies no later than, that means the death doesn't occur in here. Uh, so uh, which means up. So we can expect the death up to the age 45, but we don't want so which means for this instant we don't expect the death beyond 45 years. So it's like the probability of Tx is less than or equal to 45. So this is the area we are interested in, or the time interval. Then we can write down the probability, or the probability of death for a newborn infant, and death occurs within the next 45 years. So that is the uh, probability that we are interested, which is given in the actuarial notation. So this is also same as not 45, or if we use the survival function, it's like this. And now, so we have given the um, expression, and they have given, assuming that the survival function is an exponential function. So this is for the exponential distribution. Um, so since we have the survival function in here, we just need to substitute the value. So we know the survival function and the limit at the same time. So we will substitute this value in here like this. After using the calculator, we can directly find a value for this one, like this. So that is how we can calculate this kind of simple event probabilities using these cases. And for part B, it's a person age 20 now survives to age 38. So for the clarification, we can have age at 20 now and survives up to age 38. So our T20 starts from 0 and goes to 80. So we are not interested in this area. We need the area beyond this point. So since it is survival, simple P, and age is 20, surviving for 18 years. So that's how we can write down this. This is directly following a person who is at age 20 and surviving for 18 years. And the distribution is not given for S20. But we know that we can write down this using S0 distribution, which is 20 plus 18 divided by 20. And you can substitute the values again. Like it here, and get the corresponding answer for this one. And for part C, a person who is at age 57. So I'm drawing or illustrating the event for now because it's easy to you to digest the notation. But when you're like, I'm okay that if you're providing the answers after drawing the illustration of timeline, but it's not necessary. Um, so if you are familiar with the notation at one point of, and then beyond that, you don't have to just draw it. You can just quickly write down the notation and proceeding with the calculation. So now the age is at 57 and survives to age 60, but dies before 65. So this is the age or the event frame, a time frame with respect to age. And T57 start from 0 and goes to 5. No, since it is 57, it goes to 3, and then it goes to another 5 more years, which is 3 plus 5 for 8 years now. And with the notation, it says the probability of death for a person who is at age 57, surviving for 3 years, and death occurs within the next 5 years. So you can see that's how it works. So the TX limit is in between 3 and 8, but we are interested, the U is the gap. So U is equal to 5. T is the gap in here. So T is equal to 3 in that usual notation, and X is equal to 57. So that's how it works. And it says that the person survives from here and is not going to survive after this point. So this is like that interval calculation, which is if you got that F naught of T, so the density function, you can calculate it directly. But in here we have the survival function, so we don't need to go back to the density function and calculate this quantity directly from there. But we can skip this, and we can move on to use of survival function, because we know since it is an interval and we are interested in the distribution of S57, and it goes from 3 to S57 of 8, because the actual number line of Tx goes from 3 to 8 when we get that gap of 5. So that's how it works. And now, since we don't have S57 with us, but we have S0 with us, so we can proceed to calculate these two quantities separately. And since it's a common denominator, you just need to find three quantities and get the difference and divide it by this. So once you substitute in here. So that's how you can deal with these notations and the survival probability calculations. So if you have the survival distribution, it's easy to work with, or if you have the cumulative distribution, it's also easy. But if you have the density function, so then you have to integrate it to get that one. So that's a common example that we can think of applying these notations and finding the usual probability that we have been calculating uh, in other courses as well. So that's applying the probability part is coming from the basic knowledge of probability theory, but identifying the event and representing it using the notation is the newest part in this course. So that's how it works. So I'll always, since this is the beginning of this notation, or this is the time that we have you have been introduced into this notation. So I'll always remind you about the order that we read it. So then follow my order. So then you can get that idea quickly and digest the idea quickly. So now we can get some useful interrelations of these uh, notations using the probability theory. So the first one was we knew that f naught x, so in here we can use t because we are dealing with time. So we knew this was true. So that means uh, we can apply this into fxt and sxt as well. Eventually, this is so if you get this survival function and the density function or the distribution function into one side, so you can say the survival probability of a person who is at age x and surviving up to t years, and the death probability of a person who is at age x, where the death occurs within the next 3 years. If you get the summation, it should be equal to 1. So that's how we can think of uh, this equation. So that means if you illustrate this one, age it as x. Suppose this is the place where death occurs, and if this is kind of an intermediate time that we are interested, which is equal to t, so then the tx goes from 0 to t, and we know that, so we can find this probability and this probability. So summing up this, so if that person has lived up to this point, so then we can find the survival probability for this one, and death occurs in this area. If that person dies within this region, that means the death occurs before t. So then we can find the death probability of this area. And in either way, if you find the survival and the death probabilities for the same time frame, still you can find, so if death occurs in here, you can find survival. So in this case, this person has survived up to t years. And beyond this, we don't know the actual lifeline. Death can occur in somewhere in here. But if the death occurs in here, obviously, we know the death has occurred before the t. So that's the kind of simple illustration we can think of. And the other one is we can think uh, another event like this. So age at x and tx starts from 0. So because I need to draw some arrows over there. Um, and when age goes to x plus t, tx goes to t. So this is the first time frame we are interested in. And suppose this person survives up to this point. So then we can find the probability a person who is at age x survives for t years. So that is the value of sxt. And this person can survive up to another u years. That means t plus u. So the gap in between 0 and this point is t and this point is u. So that's how the gaps works. But the tx goes from 0, t and t plus u. So as the age goes from t plus u plus x. So that person survives up to this and death occurs after this area. So in here, now you can see the age is x plus t. That means you can find a person who is already at age x plus t. The survival probability of that person who is at age x plus t for another u years is given in here. And that is the two separate events. But if you get it, so I'll use the red line. Suppose there's another person who doesn't like see the breakdown of these 2 years. He might have seen the first person in at age x and seen him again after t plus u years. So then that for that person, he thinks that this person has survived from age x to x plus t plus u, or from tx equal 0 to tx equal t plus u. Then this probability is a person who is at age x has survived for u plus t plus u. So this is the probability of survival for a person who is at age x and for the next u plus t years. So this one is same as x t plus u, and this one is sx plus t u. So you can see the same event. If you don't observe the intermediate state, you can find the survival probability of a person who is at age x surviving for t plus u years. Or if you observe the intermediate step, then you will have two different observation states. A survival probability of a person who is at age x survives for t years, and then a person who has lived, the survival probability of a person who has lived age up to age x plus t and survives u more years. So those are the two equal cases. That means you can write down probability that survival probability of a person that is in age x from uh, tx equals 0 to next t plus u years. So that means we can say the survival probability of a person who is at age x for t plus u more years, same as, so these are independent. So the joint probability is probability of a person who is at age x surviving for t years times a probability who has already survived the years has the age of x plus t and surviving for u more years. So now you can see if you have, so if you can like separate uh, the survival time period into two uh, time windows, then you can have two different, or you can represent that survival probability using the multiplication of two different survival probability values. So mathematically, it's equivalent. So this is how we can show it. So this one, we can say that this is the probability that Tx is greater than no, we don't have to put it the equivalent sign here. It's greater than Tx is greater than T plus U, and we can write it like the probability that T naught is greater than x plus T plus U, and this is greater T naught is greater than x over probability that T naught is greater than x. So this was the definition. And even for these two, so I can write down the probability that T naught is greater than x plus t. So we saw we do this simplification in the explanation in the earliest case, where we get this intersection and we can write down the entire expression in here like this. The probability that T naught is greater than x plus t plus u over is greater than x is equal to probability is greater than x plus t, and T naught is greater than x times, for this part, now we know the T naught is greater than x plus t plus u, because it's a summation of these three terms. In here is summation of these two, and they have derived x plus t. So if you get cancel out these two terms, right hand side is equal to the left hand side. So you can see the same quantity, we partition it into a multiplication of two fractures, and by the definition, these two become um, S naught of x plus t plus u over S naught x, and for this it is S naught x plus t over S naught x times, for this one it's again x plus t plus u over Sx, and we know this is, so you can like go back in notation. So you will see this is in here Sxt plus u, and this is Sxt, and this is Sx. So we don't have to go there. So this is just a demonstration of uh, the validation or the validity of this expression. And in different notations, you can write down the same thing. So at some point, you have to deal with those. The simplification is done using the actuarial notation, but for the calculation, you obviously have to go to these probability notations where you have to substitute some known survival distribution uh, distributions if it is given, or if the density given, find survival function and substitute it here. But in upcoming topics, we will use these quantities directly using the live table. So because in the live table, they have these quantities are already being calculated. We just need to use these equations to find new values. But in this part, so we need to see how these equations are coming from. So that's why uh, we go to the fundamentals and find it. So at the end, we can say Px t plus u is equal to survival probability of a person who is at age x surviving to t years times the survival probability of person at age x plus t for u more years. So this is same as survival probability of t plus u equals survival probability of t times the survival probability of x plus t for u. So these are the possible relations we can play with. And now another equation can be found because we discussed about this um, deferred probability of death. The probability of death occur for a person who is at age x, who has already survived for t years, and the death occurs within the next u years. So tx is 0, t, and t plus u. Age is x, in here x plus t. At this point, it's x plus t plus u. So that person survives up to this point and death occurs in here. So surviving up to this point means probability of surviving with at age x for t years. And then the death occurs in this space. That means you can think like this. So this person, uh, so the death occurs in this interval. And if you think that the probability of death occurs in this large interval and the probability of death occurs in this small interval, still, if you get the difference, it will give the, because since it is an area calculation, the probability, we can think if we get the area from this point to this point and the area from this point to this point in the density function and subtract it, the resultant area is in between t and t plus u, which is the probability of death occur in between t and t plus u. And with the same motive, so we can think if that person has already survived up to this and death occurs within the next UE, so I can say the probability of death occurs for a person who is at age x plus t and within the next U years. So already, so this is the uh, death time. And that means we can think of three different ways of writing this deferred probability. So the first one, as I mentioned, if I get the death probability in between 0 and t and 0 and t plus u, then I can think because the death probability is high when the age is high. So which means higher the age, higher the death probability. So person who is at age X, the probability of death for a person who is at age X within the next T plus U year is higher than the death probability of a person who is at age X and the death occurs in between the 0 and T or within the next T's. So since this is the largest area and this is the smallest area, which is starting from the same starting point, if you get the subtraction in between these areas, you will get the area in between T plus and T plus U. So that means the death probability of a person who is at age X, who has survived for T years and death occurs with the next T years. So this is a possible way. And also, you can write down on the other way. We know that the survival function is a decreasing function. And higher the age gives you, or age, lower the survival probability. And that means the survival probability of a person who is at age X at surviving for T years is greater than the survival probability of a person who is at age X and death occurs after U plus or T plus U years. So let's use the same order. T plus U years. So this is the largest area and this is the smallest area. So if you get the subtraction from the largest from the smallest, the resultant area is the area in the interval of T to T plus U. So that is the deferred probability, death probability of a person who is at age X, who has survived for T years and the death occurs within the next U years. So this is also a possible way of writing this deferred death probability of a person who is at age X for T years and death occurs in the next few years. And the third one is the intervals, the decoding it to two intervals as I mentioned in here. It says this person who is at age X, the survival probability of the person who is at age X survives for T years and so this is X and this is the multiplication. I'll use a dot, otherwise you will get confused. So dot is the multiplication and whose the death probability of a person who has lived for X plus T years and the death occurs in the next U years. So this is another possible way of writing down the deferred death probability of a person who is at age X deferred for T years and death occurs within the next U years. So all these three quantities gives the same death probability, which is a deferred one for T years. So that's how we can write down these three different equations for the same probability quantity of death. And also, even using mathematics or the axioms of probability, so we can use the notation and prove this mathematically. So we use this graphical representation and argue about the occurrences of death and use the notation by the definition and use this. Suppose I'm using the first one. So since it's Q, T plus U, and the death probability of a person who is at age X, the next T years. And if I change the notation into the survival probability, so this one is 1 minus the survival probability T plus U, and this is 1 minus the survival probability for T. And these ones get cancelled out, and That means this is get positive, this is negative. So this comes to the first part and this comes after that. So mathematically it's correct. And also for this one, we showed an equation in here. So you can extend that one like this. The person has already survived for T years. That means you have the survival probability for T years, then the survival probability of a person who has already survived for X plus T years and surviving for U more years. Now, this is a common factor. I can take it out and it gives me X plus T, survival probability of a person who is at age X plus T and surviving for U more years. This gives survival probability of a person who is at age X surviving for T years times the death probability of a person who has lived X plus T years or age at X plus T and death occurs within the next U years. So now you can see the same, these three types are also has the same quantity because starting from the first line, we can go to the next line and go to the third line after that using the same axioms of probability laws. So that's how we can prove those things and use those without any proof in calculations directly. So the summary of these equations are given in here. Now we can proceed to calculate some quantities using the probabilities that are given in this notation. So in here, we can see for part A, we are asked to calculate the probability or the survival probability of a person who is at age X plus 3 and surviving for 1 year. Now, in the given information, we have survival probability of a person who is at age X for the next year, survival probability of a person who is at age X plus 1 for the next year, survival probability of a person who is at age X plus 1 for the next 3 years, death probability of a person who is at age X plus 3 for the next year. So if we can see by the definitions, it's easy to go with the information 4 and define this as this. 1 minus the death probability of a person who is at age X plus 3 for the next year. And it directly gives us this. Now, for part B, it says we need to find the survival probability of a person who is at age X and surviving for 2 more years. So with the information we are given, so if I illustrate this one, the age is at age X, surviving for 1 year, surviving for another year, X plus 1 and X plus 2. If I get Tx, it goes from 0 to 1 and 1 to 2. And then, so this large jump is the survival probability of X surviving for 2 years. And the two small jumps are X surviving for 1 year, X plus 1 surviving for 1 more year. So you will be ended up in the same destination point. That means I can write down the same quantity using survival probability of X for 1 year and survival probability of X plus 1 for 1 more year. That means you can get the answer using the calculator, which is equal to 975. So now you are more like you might have a clear idea about how these things works. And now we can go for part C. So I would like to give you 3 minutes to think about part C and proceed. So then after 3 minutes, I will um, solve the next three parts. So part C, D, and E, so that you can take a start for the calculation and then continue the calculation with me. Okay, so I think you had some sufficient time to try that one. So let's proceed to decode that probability. And in here, it's the probability or survival probability of a person who is at age x plus 1, surviving for 2 more years. And yeah, as usual, we can um, so write down or draw the timeline like this. The person is at age x and at age x plus 1 and x plus 2 and x plus 3. So since it's like starting from x plus 1 and going to 2 years. So this is the survival period that we are interested in, starting from x plus 1. So if the age started from 0, the tx start from 0 if the age starts from age x, but tx plus 1 start from 0 in here if the age is x plus 1. So we have two options, but the thing is we have few available information about the probabilities starting from x, but we have two more information about the probabilities starting from x plus 1, and then the second information which is in here, it gives the probability of the survival probability of a person who is at age x plus 1 and surviving for 3 years. That means this is given by this, the survival probability. And we are interested about this survival probability, which is this for this jump. And age goes to x plus 4 in here. So if we are interested in tx plus 1, the tx plus 1 goes from 0, 1, 2, 3. So gap is 3 years. So we have a familiar equation for this one. We have one large gap and we can decode it to two small jumps. So we can write down this p x plus 1. So our probability goes from x plus 1 for 3 years as the survival probability of a person who is at age x plus 1 surviving for 2 years times the survival probability of a person who has lived now since they have lived 2 years. So it's now the age is x plus 3 and surviving for 1 more year. So that is this, x plus 3 years and surviving for 1 more year. And this one directly it is not available, but you can see we have this. That means we can write down the same quantity as px plus 1 for 2 years times 1 minus q x plus 3 for 1 year. So you can directly substitute the values of the left-hand side, which is this, and this is the unknown quantity. And for this, you have this. Eventually, you will get the survival probability of a person who is at age x plus 1 surviving for 2 years by solving this equation. And for part D, it's the survival probability for 3 years starting from x. So we have two, so we can decode the interval for 3 jumps now. The large jumps goes from 0 to x plus 3, but we have x to x plus 1, x plus 1 to x plus 2, and in here we found x plus 3 to the next for the following year using this death probability given in here. That means if someone is needed, we can calculate those 3 jumps or multiply those 3 jumps and find this one. But from part C, so we can which means save those 2 jumps, because we can see if we goes from 0 to 1 in here, then we can go from x plus 1 to x plus 3 within the next jump. That means since we have calculated this already, so we start from x surviving for 1 year, and once they have survived for year, the age is x plus 1, and surviving from age x plus 1 for 2 years, which is given in part C. And you can directly find that from here. Otherwise, since we found this survival probability of a person who has at age x plus 1 for 2 years using two-term multiplication in here, so you can find this one directly with the 3 terms which is involved in this part C as well. So there are 2 possible ways of doing that. And for part E, we have a deferred death probability of a person who is at age X, who has lived for 1 more year, and the death occurs within the next 2 years. That means we know the person who is at age X has survived for 1 year, and then the death occurs for the person who is at age X plus 1 within the next 2 years. So that is the direct application of the survival relationship, the probability relationship given in the equation 8. And now for this one, we have calculated in part C, the survival probability of a person who is at age x plus 1 for the 2 years. That means we can get that probability for here. The survival probability through this expression. So once you get this probability from part C, you can substitute in here and find the corresponding probability for part E. So now you can see these relations that we discussed for the survival probability and the death probability of a person who is at age X is useful to interpolate in between intervals or extrapolate beyond an interval if we have some linked probabilities on the age line. So in here, for an example, we had probability starting from x plus 1, and x at the age of x plus 3. So we had this. So in age wise, we had information only for 3 different ages: x plus 1, and x plus 3. But we could calculate the probabilities for x year. So if you get these A, B, C, D, and E parts, all the ages were x plus 1, x, and x plus 3. So that means at least you need to get one information corresponding to the year of the age that we are interested in. After that, we can find some intermediate quantities and get multiplications, or get the complement rule and then the multiplication accordingly for our need. So that's how these calculations work for the continuous case. So in here, the definition also, I mentioned that. So this case, we consider that the capital Tx denotes the future lifetime of a person who is at age X, and that is a continuous random variable, which is a continuous measurement. So you can have 1 year, 1.2 years, 1.32 years, like that. It's a continuous measurement. But suppose you are not interested in, so in that case, so I think like I can explain why we need to think about the continuous and uh, discrete future lifetime random variables, because as I mentioned, so we are interested in these future lifetimes because we need to know kind of an approximation when the death occurs for a person who has purchased this insurance contract. So if we are paying the benefit at the moment of death, so then we need to find the approximate death time, or the probability of death occurs within kind of an at a point which is not a complete number. So then we think that suppose the person purchased this insurance when he was at age 25, and Now we need to think, so we need to find whether this person survives at for 20.5 more years. So then we need to find survival probability of a person who is at age 20 and goes for 20.5 more years. So in that case, we have to do some like fractional age probability calculations and find the probability of having that 20.5 years. So that is the our ultimate goal. But in this part, we are only calculating these for whole numbers, even though the TX was continuous, because we want to know whether we have to pay the benefit at the moment of death. So if we are paying at the moment of death, so then definitely we have that random variable is kind of a continuous random variable, and that can occur at any point in the future for that insured person who is at age 25. But if you are paying the benefit at the end of the policy year or the calendar year, so that means if the death occurs in May, the benefit payments comes in uh, December 31st. Okay, like for an example. So if the death occurs in the same year at November, and those who get the or those two policies get this benefit payment at the same date, even though it's case in January, the benefit comes in December. So then we don't have to worry about that fractional age, so fractional lifetimes in between all uh, numbered age. So then we can like calculate the discrete probabilities using a discrete random variable for the future lifetime. So in this case, we move for the current future lifetime concept of the random variable. So in the current future lifetime random variable, we only consider about the whole number or the uh, to get to decrease to get a decrease discrete value and to decretize that number, so someone can think about rounding off or cutting off. So in here we are using kind of a cutoff technique where we only consider the integer value of that continuous age. Or suppose if this person survives for 2.5 years, so then the current random variable gets only 2 as the uh, level of that random variable. So for anyone who dies within the next 2 years to 2.99 years, all these people have the same current random value for the future lifetime as 2 years. So that's the basic interpretation. So the current lifetime of a person who has lived for X years is the integer part of the continuous future lifetime of that person. And this means, suppose a 2.5, the current value of 2.5 is also 2, and current value of 2.9 is also 2. So for both these two policy holders, the current, so the TX value is 2.5 and 2.9, but the KX value, the current value is 2 for both of them. So it's kind of a, if we draw that function of a random variable from 0 to 1, it's 0. Then it jumps to 1. And from 1 to 2, it's 1. And then it jumps to 2. And then from 2 to 3, it's 2. As soon as it goes to 3, it jumps to level 3 and maintain the 3 until you meet 4. So likewise, it's kind of a step function. So this is how we can illustrate this function, the random variable or the behavior of the random variable. And that means the probabilities always gives as an interval if we use Tx. So if for this example, for the particular values we got 2.5 and 2.9, both have the same true value. That means if the probability of kx equal to 2, that means we need to take the entire probability of the interval, which starts from 2 and ends with 3. So 3 is not included for the interval, but 2 is included. But as I written down in the previous part, since Tx is continuous, so no matter what these limits are or boundaries of the interval is included or not, it always gives the same value. So that's not a big deal. We just need to find that probability using whenever we have the density function, we can use the integration. And if you have the survival function or the cumulative distribution function, we know how to find these values. So this is kind of a simple uh, illustration. So I can write down if the probability is k equal 3, which is this level, if kx equal 3, that means tx is equal to 3 or greater than that one, but less than 4. Likewise, we can develop this probability for these small intervals which has the same length. And now we have an interesting pattern in here. You can see if I can develop this one for the previous steps, I can do is like this. Okay, I'll use mm, no, so I'll use the same page, but I'll write down it from beginning. If the kx equal to 0, says it's the tx goes from 0 to 1, but it's not equal to 1. This means a person who is at age x, the death occurs within the next year. When it is equal to 1, it says the probability that the tx is greater than or equal to 1, but less than 2. That means the person at age x has already lived 1 year and death occurs in the next year. And for this one, the person at age x who has already survived for 2 years, the death occurs in the next year. And so this is the probability, and here the person who is at age x who has already survived for 3 years and death occurs in the next year. So that means if this continues to go, it's always the person is at age x, survive for so this is equal to the deferred time is equal to the value of current random variable, and then always the death occurs within the next year. So that is a constant case. We are always focusing on the death occurrence at the next year. So the deferred year is equal to the value of the current random variable. So that's how we can see a common pattern in here. So that is that relation. It can be like formulated in a proper way, like in here. So as I mentioned, if we want the death occurs in the next year, we don't use that one in here. So eventually, if I build this. This says the probability that Tx is equal or greater than to k, but less than to k plus 1. That means this person has a death probability when he's at hx, survives for k years, and die within the next year. So this is the common um, form of the probability mass function of the current random variable, and it is denoted using the actuarial notation on the right hand side. So this is the mass function because it is a discrete distribution. Now, so in the Tx, it has a continuous distribution. That's why we had the density function. So when we had the density function to find interval probabilities, we had to integrate. But if you have the mass function, which is corresponding to a discrete random variable, so you need to use summation to get probabilities, to calculate probabilities uh, for intervals. And now using these, you can get the cumulative distribution function. So okay, so in new part, so we know that the cumulative distribution function of a person who is at hx, but now so we cannot use fx actually, because as a rule of thumb we use the capital F for the continuous case, but by the definition the cumulative distribution says the current random variable is less than or equal to some k values. This means this is less than or equal to k, means the probability that kx is less than, obviously, the kx plus 1. And this is the probability of death for a person who is at age x, and the death occurs within the next k plus 1 years. So you can use the actuarial notation and write down the cumulative probability up to k years like this. So that means now you can see, if you are interested in the cumulative distribution function kx, that means in, uh, you require to use the similar quantity in actuarial notation, which is the death probability of a person who is at age x, and the death occurs within the next k plus 1 years. So just add one more year for the current value of the random variable to get the survival probability or the death probability for that one. That's how it works. So now we can think about uh, a way to solve this example, and let's go through it. Think we have sufficient space in here. So for x, k is the current future lifetime random variable, and they have given the death probability of a person who is at age x plus k and dies within the next year is equal to 0.1 times k plus 1, and it goes from 0 to 1, 2, 3, up to 9. So we need to calculate the variance of k and 3. So this says the random variable, where I'll use a new man page. So it says if that person has survived for x plus k years, or now the age is at x plus k years, and death occurs within the next year, is equal to point times the k plus 1 years. So where the k goes from 1 to 9. And the random variable we want to find in here is since it is 3, I think within the limited time, let's move it to 2. Suppose we are interested in this k and 2. So to find this one, we need to find the probabilities corresponding to this random variable. So for that one, this can get different levels. So it says either k or the 2 can be, so this is, we will get the outcome if k, we call it like k and 2. That means if k is less than 2, we get the value of k. But after that, if k is greater than 2, we always get the value of 2. That means this is kind of minimum of k and t. So this is equal to minimum of k, 2. So this random variable has, if k is equal to 0, then this one is equal to 0. Uh, if k is equal to 1, the random variable is equal to 1. And if k is equal to 2, the random variable is equal to 2. And if k is greater than 2, it's always 2. That means you can see the random variable only has two numbers, 1, 2, but including 0. There are 3 different states, 0, 1, and 2. So if to find the variance, first we need to find the probabilities of these 3. That means we need to find the probabilities corresponding to this random variable. So once we find these 3 probabilities, we can find the probability density function. So let's find the probability density function of this new random variable, where the random variable values are given in this state. So when it's equal to 0, when it's equal to 1, when it's equal to 2. So this is the quantity we need to calculate. Now, when we say that probability that k and 2 equal to 0, so it only occurs when k equal to 0. That means this event is same as k equal to 0. K equal to 0 means the person who is at age x and the death occurs between the next year. So it is 1. So in here, the k is 0. That means 0.1 is the answer. And for the next probability, for k is equal 1, the probability in here, k and 2 is equal to 1 when k is equal to 1. That means when the current value is equal to 1, which shows the probability of death occur for a person who is at age x deferred by 1 year and the death occurs in the next year. So this is the definition of the current random variable. lifetime random variable. That means the person who is at age X survives for 1 year, and after that, the person is at age X plus 1 and dies within the next year. So for Px, since we have the equation in terms of Q, so Px is 1 minus Qx. So that is given. And for Qx plus 1, it is directly accessible from this one. So you can write this notation first and substitute values in here. When k is equal to 0, Qx is equal to 0.1. And for this one, it's 0.1 times k plus 1, which is equal to 2. And now the final value is 0.9 times 0.2 is 0.18. So we have 0.1 in here, have 0.18 in here, and all the rest of the numbers for including 2, 3, 4, 5 up to 9, we always have k and 2 is equal to 2. That means we don't need to calculate the rest of the numbers discretely. So when k and 2 random variable is equal to 2, that means if we get the complement of probability that k is equal to 2, k and 2 equal to 2, or 0, plus probability that k and 2 is equal to 1, this is the same one. So this is the probability that k and 2 less than 2. So these two probabilities are calculated in here. That means 0.1 plus 0.8. So it's 1 minus 0.28, which is 7.2. Because we know that for a mass function, the summation of all the probabilities should be equal to 1. So now we have the probability mass function in here. Now we need to use our probability or the knowledge about this variance function, the expectation and the variance calculation. So we know that, okay, I'll write down it using x first. So variance of x is expectation of x square minus expectation of x to the square. So in here, the variance of k and 2 square minus, which is the variance of k and 2 is equal to expectation of k and 2 square minus k and 2 to the square. For this one, when k and 2 is 0, we know that square is also 0. And if we multiply it by the corresponding probability, it's still get the 0. So no matter, no effect from that one. And for this one, I'll quickly write down. The probability is 0.18 and square of 1 is 1. So we have that one here. And for when it's equal to 2, the probability is 7.2, and k and 2 is equal to 2. That means if you square it, it's 4. You have this. And for this one, again, 0 times 0, 0.1, 1 times 0.18, And when it's 2, the probability is 7, 2. This is the expectation of k and 2. When you square it, you have this one. And this is the final value of the variance. So we can find it after uh, simplification. So in the example, it's goes for k and 3, but I truncated it for k and 2 since we have limited time. Um, so if we had 3, so what you can have to do is just repeat this step for one more time and find the probability that k and 2 is equal to 2. And then after that, we know that when k is equal to 3, 4, 5, up to 9, all these uh, come back as the probability that k and 2 is equal to 3, or k and 3 equal to 3 in the example which is in the note. And you can find it use the complement rule, just 1 minus the first 3 probability. And in these expectation calculations, you will have one additional term added into those 2 terms and calculate it. So now we would see, so we have the new notation, but the probability calculations and the expectations are coming through the same familiar ways that we have been always used during this probability and distribution theory class. So that is, so we can stop from this point today. And yeah, I'll share the notes that I have been writing throughout the lecture today in the Google Classroom in a while. And I'll find a way to upload the recordings